Alright, on this set of notes, we're going to talk about energy, and we're going to talk about the various types of resources that we use to make energy. Most notably, we use energy for electricity or for gasoline, and this set of notes is, as I said in class, going to be broken up into several parts. These first few sets of notes will be about non-renewable resources, and then we'll have several sets about renewable resources. I'm hoping, like I said, to not make these notes too long. At the heart of what we're going to be talking about is energy conversions, going from one type of energy to another. So first, let's discuss the various types of energy we'll be looking at. First of all is mechanical energy, which has two forms, potential and kinetic energy. Kinetic energy is energy of movement. Potential energy is basically energy due to position or literally the potential to have energy. This is important because the kinetic energy is what we're going to be ultimately creating when we're burning gasoline to drive a car, and potential energy is locked up in, for example, there's potential chemical energy, but as far as potential mechanical energy, we'll ultimately look at hydroelectric dams, and that source of energy is potential energy. Energy is a key energy step in electricity production. So in a lot of different forms of electricity production, what you're going to do is you're going to burn something to produce heat. You're burning substances to produce heat. Generally, you're releasing chemical energy. This is a very important source of energy when we're talking about fossil fuels. So gasoline, oil, coal, natural gas, all of those store chemical potential energy in the bonds between atoms. A lot of what we'll talk about is various forms of electricity production, and that is creating electrical energy, which is found in the movement of electrons. Another non-renewable source of energy is splitting atoms to release the energy that's stored in atomic nuclei, and that's nuclear energy. You can kind of see the picture of the Simpsons nuclear power plant in the background. Last but not least, you have electromagnetic energy. This includes everything from visible light to X-rays to infrared energy. This is really important for the energy that's supplying the ecosystems because all of that ultimately comes from the light energy that's captured during photosynthesis. This is also important during the capture of solar energy because you're capturing energy in the form of electromagnetic radiation and trying to convert it generally into electrical energy. One of the more important ideas that relate to energy when we're talking about producing electricity or energy such as gasoline is the concept of net energy. You basically want the total amount of energy that you've produced to be large enough that it's much bigger than the amount of energy you got to put in to get out whatever resource you're extracting. So you can think of it almost like energy profit. So it's an example that I have up here. The energy that you get from burning coal needs to be much greater than that you have to use to mine it, to process it, to transport it, and to power any sort of electrical power plant. Because otherwise, you're using a ton of energy and you're not getting very much in return. That's not going to be profitable and it's not going to be beneficial in the long run. This is, of course, a unit that does require the use of math, so we're going to be working with several concepts. We're going to be working with the concepts of energy and power. So energy we're going to think of as work, so being able to do something with energy, which is what we basically use electricity for, use it to power our objects, use it to move things. Same thing with the energy stored in gasoline. You do need to know the units of energy, so the most common one that we'll probably come across is kilowatt hours. That is, like I said in class, the type of the measurement that we use when we're counting electricity in, for example, your electric bill. The metric unit system of measurement for energy is the joule. And there's also another type of unit, the BTU, which is the British thermal unit. A lot of times for us, it's mostly used to measure the power output or power usage of certain large appliances. It's basically the amount of heat you need to raise the temperature of a pound of water by 1 degree Fahrenheit. Common unit of power that you're going to see on the AP test is the watt. Occasionally you'll have a horsepower thrown in, but you generally don't need to know a conversion like how many watts equals 1 horsepower. And then another unit you'll sometimes see is BTUs per hour. But by far the most common one that you're going to see is a watt. More important energy concepts are the first law of thermodynamics. It's the law of conservation of energy. Same thing as the law of conservation of matter. You can't make it, you can't destroy it. So you have to get it from some source that already exists, and then you have to turn it into the form you need. Which brings us to the second law. Every time you change energy from one form to another, let's say going from mechanical to electrical, going from chemical to thermal, you're going to end up losing some of your energy. Not that it's destroyed, it just becomes converted to a form that it's very hard for us to get work out of. And that's generally kind of dispersed heat, like the heat you have in the air molecules around you. You can't really use that to do any work. So the more energy conversions you have to make, the less net energy you're going to end up getting out of it. So if you look at this diagram here, it shows you the relative energy used by various countries. Now on this diagram, what you're looking at is a total world usage of 472 times 10 to the 15th BTUs. All the other units are in basically times 10 to the 15th BTUs. So it is going to be quadrillions of BTUs. So we're just going to skip the quadrillion part for now. And if you look, the United States, even though it doesn't contain a very large percentage of the world's population, ends up using almost a fifth of the total world's energy. So we do use a lot more energy than other countries. You'll see that other countries that are, yes, developing countries or less economically developed countries like China and India have substantially larger populations than the U.S., but they still use a lot less electricity than we do. Then, of course, you've got Japan. Japan's got a smaller population than us, but they still use about 22.8 quadrillion BTUs. So we've got some high energy users, we've got some low energy users. So just a couple of stats, a couple of graphs that help you differentiate between how much energy the world gets from, say, oil, coal, or natural gas versus how much the U.S. gets. So you'll notice we get a larger percent of our energy from oil and natural gas, slightly less from coal, and we do get a little more of our energy from nuclear power than the rest of the world. The biggest difference that you see is in renewable energy. Yes, it does look very bad for the United States in that we use about half as much renewable energy or get half as much of our energy from renewable sources. But if you'll notice, about 11% of the 15% of the world's energy that comes from renewable sources is biomass, and that does include burning wood. So that doesn't necessarily mean that the world tops us by too much as far as geothermal, solar, wind, and hydropower go. Both the world and the United States get about 4% of their energy from those renewable resources. Now we are going to be exploring the process of electricity production because it's very important to understand how these differ from one form of energy production to the next. There are some steps that they have in common. For example, you generally produce a flow of some sort of fluid, whether it is a liquid or whether it is a gas. Very commonly it is steam, so you boil water to produce steam, but the source of the heat that you're using is often going to differ from one method of electricity production to another. There are diagrams in the next couple of slides, so if you're more of a visual person, don't worry, you'll get to see this. That flow of fluid is used to turn a turbine, and if you've had any sort of AP physics, you'll probably know that if you take a wire and you rotate it, you just spin it around in a magnetic field, that actually produces electric current. So the fluid that you've produced turns a turbine that's connected to a wire that then rotates in a magnetic field, and that is ultimately what makes electricity. If you look from the left to the right of this diagram, notice on the leftmost part you have a place where steam is entering this turbine generator, and that steam is going to then turn these turbine blades. As it passes through, it turns the turbine blades, which then turn a wire inside of a magnetic field, and that's where electricity comes from, just as the steps stated on the previous slide. Now we're going to talk about our several methods of non-renewable energy, which you see listed here. So three of what we're going to talk about are fossil fuels, and then the last one is nuclear power. Same information as on the previous slide, just probably a blank or two for you to fill out on your notes. Non-renewable resources are defined as resources that we cannot replenish within a human span of life. So while it's true that there may ultimately end up being more oil or coal or natural gas preserves formed over the next several 100 million years, that's not really practical for human usage. So for all these non-renewable resources, we have a term called the reserve life. And that's the amount of resources that are thought to be economically feasible, meaning it's not going to cost a whole buttload of money to extract them from the ground. We can put that in terms of how many years we have left of a certain resource. So, best example I got for you, at the current rate at which we're using it, we've got about 50 years of oil left. So our reserve life for oil as a planet is about 50 years. To the most prolific by far of the non-renewable resources, we're going to talk about fossil fuels. First up, we've got coal. To help us understand why it's going to take so bloody long to make more of this stuff, let's look at how coal is ultimately formed. So about 290 million years ago, the Earth was covered by a lot of swamps. And when trees, when plants, when vegetation died, it ended up falling into these swamps and it wouldn't get decomposed all the way. Then it would get buried under layers of dirt and rock and sediment and basically got covered by enough of this stuff that it ended up becoming compressed or pressed in by a lot of the above layers. So there was a lot of pressure there. As it got buried, there was also extra heat that was helping kind of, you could say, cook this matter. And so it's the remains of, like they like to put in cartoons, old dinosaurs, dead bodies that got cooked under lots of heat and pressure, and that is what forms coal. The longer it cooks or the greater the pressure, the greater the heat, the harder the coal you make and the higher the energy content. So coal takes a lot of time to form. There are three different types of coal, each of which has different heat content. So you have something called peat, which is pre-coal. If you've ever had to read something like Wuthering Heights, they may talk about burning peat fires. So it was used before coal as kind of a source of heat. There's some places where there's not a lot of firewood. They may still use peat for heating. You can think of it as pre-coal, and it doesn't have a lot of heat content. Then, as you compress peat, as it gets put under more pressure, you can form lignite. That's the softest coal, and it's got the lowest heat content. So it's got more heat than peat, haha, that rhymed, but less than the other types of coal. Next up, you have bituminous. It's still soft. It does tend to have a lot of sulfur in it, but it's harder than lignite. Got more energy in it than lignite as well. This is about 50% of what we've got left in the United States. Anthracite is the most desirable coal. If you can come across a pocket of anthracite, you're going to make some money. It's very hard. You can't scratch it very easily, and it's got high heat content, meaning if you burn a gram of anthracite, you're going to get a lot more heat than if you burned a gram of bituminous coal or lignite. Unfortunately, this only makes up 2% of what we have left in the United States. This graph, or this image, shows you where a lot of the coal reserves are in the world. So you have scattered pockets spread throughout kind of the middle of Eurasia, but by far the largest reserves that we have are in Russia. They're in Siberia, however, which is very cold, which means that it's going to be harder or less likely for us to get to those resources until we get more desperate. There are large smatterings of coal in the United States, most commonly in the northeast area, which is the Appalachian Mountain region, which is a part of the country that's pretty well associated with coal mining. And then if you look, there's also a chunk in Australia, but another reason that that is harder to get out of the ground is because that's very harsh desert land out there. So it's not like you can send a ton of miners out there easily. You're going to have to pay someone a lot of money to go mine out there. So in North America, By far, the major reserve of coal that's been mined throughout the years is in what's labeled as the Appalachian Basins. So the Appalachian Mountains are well known for being coal mining country. You don't tend to think of, for example, if you look at where it says Gulf Coast lignite, you'll notice it's in like Louisiana, Alabama, spreading down into Texas. You don't really think of Texas as coal mining country. We're more stereotypically known for oil and now more and more for natural gas. There's also some out in the west. A lot of that area is probably national parks, and a lot of it's desert area. So it's probably going to be a little harder to get to mine out of the ground. So this graph is just showing you the difference in state usage of coal. This is per capita state usage, and per capita means per person. So per person, the most coal is used by people in Wyoming. And if you think about it, it makes sense. Coal is very commonly used for heating, and where's it really cold? Well, up in Wyoming. You'll notice for Texas, we use about 5.4 tons of coal per year per person. But you've also got to think about the fact that we've got a higher population than Wyoming. So the amount of coal that we use as a state may exceed that of Wyoming. I'm showing you tons of graphs. If you will look, this graph has two y-axes. On the left-hand side, you have the millions of tons produced. And then on the right side, you have the years. So on the left-hand side, that axis goes with the production of coal. You'll notice you have 4 years worth of production here for 9 different countries. Then on the right at y-axis, you have the reserve life of each of those countries. So compare the reserve life to the production. If you'll notice on the far left, you have China. China has dramatically high production rates, but because they're using their coal at such a fast rate, as they're rapidly becoming more industrialized and building more industry, they're dramatically decreasing their reserve life. The United States, we've got probably about a good 250 years of coal left, whereas China's got less than 50 years. You'll also notice that Russia has the highest reserve life. They've got a ton of coal. They're not using it as high a rate, and so they've got about 500 years of coal left. Now we have world coal consumption broken up by region. So if you look from 1997 to 2006, the trend is North America is not significantly increasing the amount of coal that we're using. Neither is the Europe-Eurasia region. But if you look, it's the Asia-Pacific region. Specifically, China is responsible for a lot of this increase in coal consumption. Like I've said, they're trying to increase industry very rapidly and basically building more power plants, and these tend to be coal-fired power plants. So China's using a lot of coal. We're going to talk about how we get coal out of the ground. That's the extraction side of things, and then how we try and clean it up a little, which is the purification side. You don't just get coal out of the ground and it's nice, ready to burn, throw into a power plant chunks. You've got to do some work on it first. There are several types of mining. There's strip mining, which we're going to encounter later on when we talk about other types of mining as well, and there's contour mining. We're going to talk particularly about strip mining. What you have to do is you're basically peeling layers of rock, of soil off the surface of the earth. You've also got to remove any overlying vegetation, and this is used for really shallow deposits, stuff that's really close to the surface. So you basically take some bulldozers, you start scraping off the surface of the earth. This has huge environmental consequences, though, because you're disrupting an entire ecosystem while this mining is going on. You've also got to find a place to put all that rock and dirt that you've moved until you're ready to go back and dump it back into the open pit or the open mine where you've been digging out coal. And this requires a lot of heavy machinery to do. The other major type of mining is underground mining. So there are two major methods. We're going to look at some diagrams of them. There's room and pillar mining, where you're digging underground and you're going to dig out these large chunks of coal, but you're going to leave what look like pillars of coal behind to help keep the roof stable so that it doesn't collapse in on you. When it does, that's when you get these mine collapses that you may sometimes hear about on TV. Miners can get trapped, people can die. It's nasty business. Then there's also long wall mining, where you basically take a machine, it's going to start scraping coal off the basically from underground, and what'll happen is as this machine moves forward, you just let the tunnel collapse behind it, and you kind of don't worry about getting more coal out of that area. So this diagram shows you both long wall mining and it shows you room and pillar mining. So if you'll look there, the labels will let you see what's going on. You've got the pillars down at the bottom. Those are those large squares of coal that are left behind, and all the spaces that kind of look almost like hallways in between that, that's where the coal has been dug out. Long wall mining you see on the left, where you basically have this machine running along scraping off coal. It runs into a conveyor belt, and that gets carried up to the surface. Now, sometimes what you can do is if you're especially desperate for coal, you can dig out the pillars behind you. So you've gone all the way into the mine, you've hit all of the coal you can, and the only coal that's left there is in the pillars. So you'll start pulling out the pillars at the back of the mine, letting it collapse until you move forward until you're like right at the entrance to the mine, and then you take out the last pillars. But there's some environmental risks we'll talk about in a couple of slides with that. Unfortunately for us in the United States, the region in the Appalachian Mountains, where a lot of the coal mining has traditionally been done, a lot of the coal that can be taken out has been removed. So what they've moved on to is now what's called mountaintop removal. It's very controversial, and it makes dramatic differences to the landscape and local ecosystems. So what they basically do is they're going to cut down all the trees on a mountain. They're going to use a bunch of explosives, and they'll use that to loosen up the layers of rock, loosen up the dirt. Then they'll take these huge machines and they'll dig away the topsoil and get it hauled away. A lot of times they'll dump it into a neighboring valley and fill it up. Then there is what's called a dragline, a large machine that basically just kind of scoops up and moves the dirt aside so they can get to coal. And then they basically start digging out coal. So they blow up the top of a mountain. And if you'll look where it says on the diagram, I know the the font is a little tiny, but if you look where it says coal seam, under where it has the labels for 1, 2, and 3, which show you the steps of the process, that's probably around the level of the mountain that you're going to see. So if you look up to where it says former mountain contour, you're going to lose a lot of your mountain, you're going to be destroying the entire ecosystem, and you're going to be changing the topography. You're going to be changing the surface of your area, which is very dramatic. Here are the two major effects that you get with mining. So when you're digging underground, you can start interfering with the groundwater and the water table. You can even have stuff leak into the groundwater, and then you have contaminants that's poisoning some of the water that people are taking to drink. Another big issue is what's called subsidence. Subsidence is basically when you have an underground mine and everything collapses and falls in, and it leaves these big kind of dips or depressions in the surface. So it's like a giant sinkhole. So imagine that you were sitting there tunneling under something and the tunnel just collapsed. That's subsidence, and if it ends up collapsing enough stuff above ground, that can damage what we call infrastructure. Roads, buildings, all of that stuff that we have on the surface that we kind of like to keep intact. So the next step to purify, you've got to remove any foreign chunks of material. You don't want random rocks in there. Burning rocks isn't going to do you any good. Sometimes the coal is crushed to allow it to burn faster, and then sometimes it's washed to remove contaminants. You can also treat it to remove sulfur as well, because sulfur burned in coal is a really big problem. In this diagram, what you see are the major parts of a coal-fired electric power plant. So what you see is you see coal going in at the left, it goes into a furnace, you burn it, and the entire purpose behind that is you're getting steam made. That steam then goes to a turbine. When it goes to the turbine, it turns it. That powers a generator that makes electricity. In the meantime, from the coal that you've burned, you're releasing a lot of carbon dioxide into the air. And then also, you're going to take that steam that you produced when you burn the coal, and you're going to send it through a cooling tower so that the water can cool down, and you're going to have some steam that's going to go into the air from there too. So I put clean for clean coal in parentheses because it's relatively clean coal. So coal is basically washed to remove any impurities. This is supposed to help reduce the negative consequences of burning coal. And then also, you can remove sulfur dioxide, which is the major sulfur product that's made from burning coal, from the gases that come out of the chimneys, which are also called flues, F-L-U-E. There are also some methods by which they try and capture carbon dioxide from these gases as well. Just a couple of terms that are helpful to know when you're talking about burning coal. A flue, F-L-U-E, like I said, is a smokestack. It's a chimney. That's where you're going to see stuff, the smoke and gases coming out. What's going to be making up a large part of the smoke that comes out of a power plant is fly ash, which are very small particles, small pieces of dirt, of dust, of ash that are released in the smoke that's coming out. This is called particulate matter, and most coal-fired power plants are supposed to use things called electrostatic precipitators to attract these charged particles and to keep them from going into the air. Because if you start breathing these in, these things can cause a lot of problems with your respiratory system, and they have other negative environmental consequences too. Another thing that happens to try and clean up the process of coal combustion or burning of coal is what's called flue gas desulfurization. So as I mentioned, sulfur is a big byproduct of coal burning, and the problem with sulfur is that it ends up going on in the atmosphere to form acid rain. So what some power plants have, or what more and more power plants are having, is these chambers. They're desulfurization chambers, often called wet scrubbers. So they'll let the gas from the flue go through this chamber where it's basically got water blasted at it, which is supposed to help dissolve the sulfur dioxide and any sort of particles that are in the smoke. That stuff gets washed down to the bottom. It forms this slurry or sludge. Both words should bring to mind nasty, ooey gooey stuff, because that's basically what it is. And then you've got to take that and you've got to dispose of it somewhere. So you've got to trash it in a place where it's not going to cause environmental problems. On the combustion side of things, there are a lot of environmental effects. So any sort of ash, any sort of desulfurization sludge that you make is going to be very harmful materials that you don't want to just take and dump in a landfill. A lot of times they include some heavy metals that we'll talk about later when we talk about effects on human health, are very harmful to humans. Also releases particles into the air. That's harmful to human health and to the environment. And sometimes if you have this fly ash spill, then it can actually destroy entire homes. It can contaminate waterways. And it's actually a large source of radiation. So that's a large source of radiation that's caused by humans. Then, if you have high sulfur coal that's being burned, then that can lead to acid rain. If you are taking water out of a river that to used to create steam, then that's going to affect the water flow through the river. And of course, there's always the carbon dioxide angle. Burning coal, burning any fossil fuel, produces a lot of CO2. Just in case you didn't believe me, this is a picture, an aerial photograph of an ash slide where basically this fly ash ended up escaping from the confines wherever it was put in a power plant, ended up sliding into a local river, and this was back in 2008. So this is a massive amount of damage, and it looks like a really large bunch of nasty stuff going into the waterway. Not really something you'd want going into your local river. One thing that can be done with coal is you can actually take it and chemically change it so that it becomes synthetic natural gas, which basically means man-made natural gas. It can be turned into methanol, which is a type of alcohol. No, not the type you drink. Or it can be turned into synthetic or fake man-made gasoline. There are a number of benefits to doing this. One, makes it kind of easier to transport the energy that you get in the coal. Two, it is supposed to produce less air pollution, although I'm not sure whether that's less air pollution than coal or than traditional gasoline. It can extend our supply of oil for a couple of hundred years, which is basically a solution to a big worry a lot of people have, since we're mainly an oil and gasoline-based economy. And it can produce gasoline, it can produce diesel, it can produce kerosene, and then you don't have to send this stuff through a refinery either. However, there are a lot of negative aspects to synthetic natural gas. You don't get a ton of energy from it because you have to use energy to convert the coal into synthetic natural gas or syngas. It's expensive to make the plants that will do this, and it just exchanges one problem for another. Instead of using up our oil really, really quickly, now we start using up our coal more quickly. It's also going to make the price higher since you have to use more energy and more money to make this stuff. At this point, we're going to end part 1 of the notes. Part 2 of the notes will be put up soon, I promise, and it's going to include oil, natural gas, and nuclear power.